So Kris has been doing Monte Carlo methods from his childhood, I think. He did his PhD at University of Ghent, and then moved to, as a postdoc, to the founding fathers of the field of Diagrammatic Monte Carlo, namely Nikolai Prokofiev and Boris Vistunov in University of Massachusetts. And since already many years, he's been an associate professor at École Normale. And one of the claim to fame of the methods that Kris and also Felix Werner developed has been, for example, to establish the equation of state of the unitary Fermi gas in the continuum. And so his talk today is going to be in particular geared at applications of Diagrammatic Monte Carlo to cold atomic gases. Thank you, Kris.
Okay, thank you very much for the introduction and for organizing this really nice mini workshop, I would say. So I will be discussing Diagrammatic Monte Carlo, especially in the context of models which are relevant for experiments with cold atoms. And let me first start by acknowledging many of the people who have contributed to the things I will present. So in the room we have also Felix Werner and Michel Ferrero. And so I will first start by quickly discussing the BEC-BCS crossover. So here the system is a system of spin 1/2 fermions in 3 dimensions in continuous space. Okay? And we have a short-ranged attractive interaction. So what happens then if this attractive interaction between spin up and spin down is very weak? You will have the formation of Cooper pairs, and these Cooper pairs will form a BCS superfluid at low enough temperature. If you go to the opposite limit and you say up and down will have a very strong attraction, then there will be the formation of molecules between up and down, so bosons, which again will both condense at low enough temperature, again forming a superfluid. Now it's known since many years that there is a crossover between BCS regime and BEC regime, and in particular there is a region of that is where the system is strongly correlated, and it's very difficult to establish any accurate theory. So I will be focusing on a special point which is called the unitary gas, where the S-wave scattering length A diverges. So in this case, one might expect that there is actually universal physics because there is no length scale coming from the macroscopic interaction. And this is the system is interesting because it can be realized in cold atom experiments, in particular, for example, with lithium-6 atoms, where one takes 2 internal states for the electron, and the interaction can be tuned by Feshbach resonance. So this allows really to do an accurate comparison between theory, which is in the zero range limit, and these experiments. So let me immediately, since I don't have too much time, let me immediately jump to diagrams. So for example, we are typically interested in an intensive quantity. Let me call it Q. This could be the pressure, which is just temperature over volume times the partition function. And then we make an expansion, for example, for the pressure into Feynman diagrams where AN will be the sum of all diagrams of order n. Now the model that we use, first of all, will be on the lattice, and this is just to avoid any UV divergences, which happen typically in the continuum. So to avoid that, let me first say that there is a kinetic term where K is restricted to the Brillouin zone. And then also we have an on-site attraction. So G0 is the attractive on-site interaction, and B is the lattice spacing. So then we can make an expansion with respect to G0, and this would lead to some Bayer scheme, which works only on the lattice, where diagrams are built from the single particle propagator G0 and the capital G0, and little G0 will be the interaction vertex, or the interaction strength. And these are typical diagrams for the pressure at order 1 and order 2. Now, this doesn't work immediately in the continuum, so if we want to do the calculation in the continuum, we can use the following trick. We can sum a subclass of diagrams, which are known as ladder diagrams. These are basically the diagrams which are relevant to the two-body problem. So if you have 2 particles in vacuum, you will just have only those type of diagrams. These can be summed basically analytically to give some bosonic pair propagator gamma naught. And now the nice thing about this gamma naught is that it's well defined in the continuum. So here we can take the lattice spacing B going to 0, G naught, the bare coupling constant, will also going to 0, and we fix the scattering length to be infinite. So then we can define or construct diagrams, Feynman diagrams, built from the single particle Green's function G naught, the free single particle Green's function, and this pair propagator gamma naught. Okay, then we have to exclude a particular set of diagrams where we have these ladders here, because these ladders are already included in gamma naught, otherwise we would double count. So that's one scheme we used, so I will refer to this scheme as the ladder scheme. And then secondly, we also used the so-called bolt scheme, where we look at a series in Feynman diagrams, both for single particle self-energy and two particle self-energy, where all the lines are fully dressed. So this is the fully dressed single particle propagator, this is the fully dressed pair propagator. Of course, we don't know these a priori, but they are solutions of the Dyson equation for the single particle and two particle channel, and this we have to do it self-consistently. So we are summing these diagrams by diagrammatic Monte Carlo, and at the same time doing this self-consistent cycle until it converges. All results for the BEC-BCS crossover, or for the unitary gas that we have published so far, are used to this first generation of diagrammatic Monte Carlo algorithm, where we actually still, or where we did the sum over topologies in a stochastic way. So we have some Monte Carlo process where we have a diagram at particular order, the particular topology and values of internal variables. In this case, these were momentum imaginary times. And then there are Monte Carlo updates doing a random walk in this space in this way, performing this sum and these integrals. So here is the result if you don't do anything. So you just, this is the ladder scheme, and you just make an expansion in gamma naught. This quantity is called the contact, or also Tan's contact, or two-body contact. It's basically a quantity which is related to the short-ranged physics. Okay? It can be obtained by looking at the momentum distribution, which will have k, 1 over k to the power 4 tail at large momentum, and the prefactor is the contact. You can also get it from the pair correlation function or the pair propagator at position 0 and time equal to 0 minus, which tells us that it's kind of like a density of pairs, if you wish. So this is the contact times thermal wavelength to the power 4 as a function of the cutoff in our diagrammatic expansion, and basically the series doesn't converge. Slight depression here for some months. But there is a cure. It's not easy, but so what do you do if this series diverges? Well, you can do the following. A priori, it looks a bit formal, but you can do the following construction. You can construct some function q of z, okay, such that if you Taylor expand around z equals 0, you get a Taylor series whose coefficients are just an, the sum of all diagrams of order n. And then q of z equal 1 should also give the physical quantity q, the pressure, for example. So it's possible to construct such a function q of z, which is not a priori not obvious, but let me give you an example here in case of the ladder scheme. So here you have basically the log of the partition function, where phi's are bosonic are Grassmann fields, and etas are bosonic fields, so just complex fields. And then we have an action where we recognize the propagation according to gamma naught, the free propagator, single particle propagator, and we also recognize the propagation of pairs according to gamma naught. And then they are coupled. Okay, so this allows us to construct this q of z. Then the big question is, given these coefficients, which we calculate with diagrammatic Monte Carlo, can you get back the function at z equal 1, which is the physical point? Well, I will really make the story quite short, but first of all, the first thing we had to understand was how does A of n behave at large order? And knowing this action which I just showed, this allowed us to use an instanton method and calculate the large order behavior of these coefficients an. where we found that they scale at large order as n factorial to the power 1 over 5. Okay, so there is some cancellation of diagrams, but it's not complete. Moreover, this means that the radius of convergence is 0, the series is asymptotic. However, knowing this behavior, we were able to construct a resummation technique, which in this case is conformal Borel resummation, which uses this behavior and allows us to get back the function q at z equal 1 in a unique way. If you want to know more details, it's explained in this paper here. So let me show you results. So this is the same plot as before, where I have this contact as a function of the maximum order in the diagrammatic series. And now we have the ladder scheme and the bolt scheme after using Borel resummation, and they nicely converge to the same value. This is T over Tf 0.6. So this is in a normal phase. The superfluid phase, the critical temperature is about T over Tf 0.19 or 0.16. So here I show the density times thermal wavelength cubed as a function of the maximum order in the diagrammatic series. Again, after Borel resummation, it converges. And I also show 2 points here, which this is just a zoom of an experiment which was done in the group of Martin Zwierlein with ultra-cold lithium-6 atoms, where he measured the equation of state, and we see a perfect agreement without any fitting parameter between theory and experiment. So this is T over Tf 0.6. If we go to a lower temperature, T over Tf 0.2, which is fairly close to the critical temperature, then different schemes give a result which is consistent with the experimental value. So here you see this contact in units of Kf to the power 4 as a function of temperature. The critical temperature is indicated here. So here the system goes from normal to superfluid, and the blue points are diagrammatic Monte Carlo results in perfect agreement with 2 different experiments, one in the group of Martin Zwierlein and one in the group of Kris Vail. Okay, so this was what I wanted to tell about the continuum case. Of course, our next idea or our next wish was to enter the superfluid phase, and then even possibly calculate the contact here in the superfluid phase. However, we know that in the continuum, typically the series will be asymptotic. I would say that this is the generic case for the continuum. So to avoid these problems of having to understand how to Borel resum the series, we went first to the lattice case. So that's why we focused on the 3D attractive Hubbard model, but in the superfluid phase, so in the phase with broken symmetry, just to separate the problems of having to deal with 0 radius of convergence and broken symmetry. So let me briefly explain the setup. So here we have the 3D attractive Hubbard model, which we have seen before. The only difference that it's here, it's in 3D and U is negative. So how can we enter the phase of broken symmetry? Well, the order parameter here is a BCS superfluid. The order parameter is just C, the annihilation operator for up times down at position 0. And we have to expand around an unperturbed quadratic Hamiltonian, which has U1 symmetry broken. So that means that we take the hopping term of the Hubbard model, and then we add basically a mean field BCS term, which has this symmetry broken. Then we construct the Hamiltonian H, which depends on a formal parameter xi, which is just 1 minus xi times this quadratic Hamiltonian plus xi times h, and h is the full Hubbard Hamiltonian. So if we take xi equal to 0, we just have this mean field BCS theory. If we take psi equal to 1, we have the full Hubbard model. So then the idea is to just start from mean field BCS theory and systematically include corrections to it until we arrive at the superfluid phase for the Hubbard model. So then we can define here Q of xi, which is the expectation value of some parameter, let's say some quantity, let's say the pressure, with respect to this h xi, Taylor expanding psi, and we can calculate these coefficients Qn, where here we will use the CDAT algorithm, as I will show in a minute. Then the idea is, of course, that you need to have xi equal to 1, which is the physical point. And if the series is convergent, this will be guaranteed by if you just sum all of these coefficients, you should get this, which works by Abel's theorem if the series is convergent. So in practice, we did this for the pressure. Okay, so I'm just repeating here the same thing, but using the pressure as Q. Okay, this quickly to flash, but I will not explain the details, but the idea is that we will use the CDAT algorithm, okay, which means that we are looking at all the possible diagrams, and the disconnected diagrams are removed by this recursive formula, okay? And the computational cost will be 3 to the power n operations, so exponential, not factorial. And the big difference between the calculation and the normal phase is that we have these we have this numble formulation where we notice that we have propagators like psi dagger up, psi dagger down, which have a non-zero expectation value. And this means that, okay, the symmetry is broken, and this corresponds to what is called anomalous propagators. So there will be anomalous propagators in the diagram. So we used the fast Feynman diagrammatics library, which was written by Riccardo Rossi and Fedor Simkovic. Okay, so the first thing we tried to do, or we did, was to really get a benchmark to a case which is solvable by other methods. And in this case, let me call mu up and mu down, so the chemical potential for spin up and spin down, as mu plus h and mu minus h, h being the Zeeman field, hopping 1, u equal to minus 5. And let's be around quarter filling. So then AFQMC in this case, because chemical potentials are equal, so h is 0, it doesn't have a sign problem, and one can calculate the critical temperature between the normal phase and the superfluid phase, and you see that at the value of u of minus 5, the critical temperature is 0.25, so in units of TF it's 0.06. So it's not at all at weak coupling, I would say it's a rather intermediate coupling. And then let's compare with a sign problem-free quantum Monte Carlo method. So here you see the results of a temperature which is half of this critical temperature at u equal 5. So TC0 remains this just means the critical temperature for h equal to 0. Okay, so let's go to half of that, which is 1 over 8 here, and this is the series as a function of the maximum order of the diagrammatic series for the order parameter. So we see that it converges. We can extrapolate. Of course, you get some error bar from extrapolation. And then we compare with, in this case, determinant diagrammatic Monte Carlo. So this is a method which works, which is an expansion in Feynman diagrams for the partition function. So in this case, you have all diagrams, both connected and disconnected, but it can only work for a finite system. So you cannot take the thermodynamic limit. So this is this determinant diagrammatic Monte Carlo method as a function of L, the linear size of the system, where you have to just make L bigger and bigger, and then ultimately you reach the thermodynamic limit, and we have a nice agreement between the two methods. So then the obvious next step is to go to H Zeeman field non-zero, and there basically there is nothing to compare to because typical conventional quantum Monte Carlo methods have a severe sign problem. And what is the phase diagram that one expects? So this is based on mean field theory. Basically, again, we have just a superfluid regime and a normal regime. If you introduce the Zeeman field, of course, you will disfavor pairing because you will try to break up pairs. And ultimately, if H is too big, because not every fermion will have a partner to pair, there will be a transition to the normal phase. And at low enough temperature, it will be first order, and higher temperature, it will be second order. So now I will present results of a scan going like this at TC0 over 4. Okay, so we expect that if we increase H, we should see the first order transition from superfluid to normal phase. This is the pressure, or minus the pressure, which is nothing else than the thermodynamic potential. In blue are results for the superfluid regime, meaning that we include delta 0, so a term which breaks the symmetry. And the green results are also diagrammatic Monte Carlo results, where this delta is chosen to be 0, so no broken symmetry, or the normal phase. So at low enough Zeeman field, you see indeed that the superfluid is stable. It has the lowest thermodynamic potential. And then at some critical value of H, there is a crossing of the two, marking the first order transition from superfluid to normal. So we could determine this critical value of H. Another remark is that the spin polarization, so the difference between density up and down, is related to the derivative of this pressure. So this curve is pretty much flat, meaning that the system is not polarized at all for this temperature. Okay, here is mean field. So mean field is qualitatively correct, but quantitatively quite off if we compare results to mean field. So this is what I have presented so far. So this is temperature, Zeeman field. We made this scan and we see the first order transition. Then we did the second calculation. Here inside the superfluid regime at a higher temperature where we did see a spin polarization of the system. It's low, but it's there. It's around 4%. Okay. Okay, so I think I have 5 minutes. Or
yeah.
Okay. 7. Okay, so in the remaining time, I will discuss another problem I have worked on, which is related to these two other bigger projects, and that's the Fermi polaron. So in this case, this is also relevant for experiments with ultra-cold atoms, because basically you have this BEC-BCS crossover and temperature, which I discussed before, but then you can also try to spin polarize the system, okay? And if you go to very, very high spin polarization, ultimately you end up with having only a few spin downs in a C, an ideal Fermi gas of spin up fermions. And this is the Fermi polaron. So if you have only one such spin down. So the Fermi polaron is a mobile impurity immersed in an ideal Fermi gas. And what happens in this case is that if, so you turn on the attraction here between this impurity and the particles of the Fermi sea, and due to this interaction, this impurity will be dressed with excitations of the medium. Excitations of the medium here are particle hole excitations of the Fermi sea, and this is called a polaron. So it's just a particle dressed with particle hole excitations. And now what can happen is that if the attraction is very strong, it's not guaranteed, but it might happen, that this impurity will form a bound state with one spin-up fermion of the Fermi sea. So it will be a dimer or a molecule, and this molecule will again be dressed with particle hole excitations of the Fermi sea. So you have a transition from polaron to what is called dimeron, just a dimer with particle hole excitations. And this was indeed seen both experimentally and also predicted in an early paper by Nikolai Prokofiev and Boris Vistanov. This was basically the first paper using Diagrammatic Monte Carlo for a fermionic problem. Here you see, for example, this crossing. This is the energy of the polaron. This is the energy of the molecule. And indeed, there is a critical value of the interaction strength where both branches cross. So this is the ground state energy, okay? We did the same calculation in 2D. Basically, the same happens. In 2D, there is also a transition. This is the polaron energy. Strong coupling corresponds to this eta being large and negative. And beyond some critical value of the coupling, the system makes a transition to a molecule state. So what we realized then is, or what we wondered at some point is that, okay, can we use CDAT to try to solve the polaron problem? And we realized that CDAT actually tremendously simplifies in this problem and becomes remarkably simple. And the reason is the following. So the diagrams are basically the following. So you have a single spin down, which is created at space-time equal to 0. It's an impurity, so it can only move forward in time. Then it will interact. This block here is the gamma 0, which I introduced at the very beginning. So it's a summation of all other diagrams. It will move forward in time. It can interact again, move forward in time. And then at some space-time point x, it will be annihilated. So it's a single particle propagator. Now, to get all the contributions, all of these lines need to be connected in all possible ways. And that can be done by a single determinant. And now it's not a surprise that there are no disconnected pieces, because this line connects all of the different connections which are made for the spin up. So the algorithm is just simple: integrate over these space-time coordinates, you have the product of propagators, and a single determinant, so no recursive formula. The only additional trick is that you need to avoid double counting of ladders, which can be done by setting some matrix elements to 0. And in this way, you avoid double counting. So this is what we get. This is the nth order contribution to this Green's function as a function of diagram order. So here, we could go to order 30, for example. The series seems convergent. However, if we zoom here in this region, this is for scattering length infinity, actually the series isn't convergent. It's slightly, well, it's exponentially divergent, but the prefactor is small. So it's a very small amplitude. Meaning this implies that the radius of convergence is actually finite, and we are slightly outside of the radius of convergence. And this, we could fix it with a conformal map. I don't have time to explain the conformal map, but it's a well-established technique. And doing this conformal map, so this is the energy of the polaron, again as a function of order, we could really have a convergent series for KFA infinity, claiming a very high precision for the polaron energy, which can now be a benchmark for many other many-body techniques which have been used to study this problem. Okay, I will take maybe 1 more minute to say a few words about the last project that we did. This was in collaboration with Gérard Pasquale and Jordi Borona, where we basically asked, okay, what happens if we put the polaron on the lattice? So we look at the attractive Hubbard model here in 2 dimensions, having only a single spin down and many spin ups. Naively, one would think nothing special will happen because it's at low filling, you should retrieve the continuum limit, and okay, there is a lattice, but maybe it's exactly the same. Well, there was actually something interesting that we found. So we made an expansion as before using this PDET algorithm. Here we can make an expansion in bare U. We don't need to do this regularization because we are on the lattice. The first remarkable thing that we found is that we didn't see any sign problem. All contributions were positive. This allowed us to go to very high values of U, orders 200, without big effort. And the second thing was that, so I want you to look only at the data with the arrow bars here. So this is data for the polaron energy. This is data for the dimeron energy. And as a function of U, for U's up to -20, for a filling fraction for the spin-ups of 0.3. And basically, we don't see any transition. So the transition which is there in the continuum isn't here. It's always the polaron state, which is the ground state. So then, if you vary this filling and go to low enough filling fractions, you should retrieve the continuum limit. And indeed, at low enough filling fraction, there is a transition from polaron to molecule at strong coupling. Then, if you increase the filling fraction, this transition shifts to higher values of U, and ultimately it shifts to infinity, and the transition disappears, what you see here. And then something, I mean, then this implies that if you're at very strong coupling and you will increase the filling fraction, then you will have a transition from, at first, you will have a dimeron or dimerons, and then there will be a transition where the effective particles or the quasi-particles are polarons at same value of U. Okay, so let me just mention a few open questions, or there are actually a lot of open problems still to be solved. For example, for the unitary gas, we did so far only the normal phase, but even for the normal phase, there are what happens in the polarized gas, look at the spectral function, enter the superfluid phase, is the series Borel resummable, yes or no? Could we, for example, use variational perturbation theory, as was done for the electron gas by Kun Cheng and Christian Hall? Then for the Hubbard model, one interesting option could be to use ladder diagrams to be able to go to stronger coupling, maybe, as was done in this paper, in a paper by Fedor Simkovic and collaborators. Look at polarized superfluids at 0 temperature. Look at 2D, where we can have a BKT transition. And then the project which we are mostly interested in now, where we have our postdoc Nils Chachi also in collaboration with Ricardo and, sorry, on this picture, a very young Felix, where we look at FFLO, or this is for the attractive case, FFLO, but this maps onto stripes for the repulsive case, where we start from an H0, so a quadratic Hamiltonian, which has the right broken symmetry to see stripes, or competition with D wave, where we, as we have also seen in the course of Antoine, need to include the right term which breaks this D wave symmetry. And with this, I thank you for your attention.